Hello everybody. So today we'll discuss about three-phase transformers, the concepts which we have developed till now in the topic of transformers, everything, the working principle, equivalent circuit diagram of transformers, then efficiency, voltage regulation of the transformers. Then we talked about auto transformers, per unit systems, everything. So those concepts are equally valid for three-phase transformers as well. So generally there are two ways of getting or manufacture generally there are two ways of making three-phase transformers. One way is either using a bank of single-phase transformers, okay, where you have three units of single-phase transformers and you connect it as per your requirement to form a three-phase transformers, okay. And the other way is either use a single unit of three-phase transformers where you generally we use core type or shell type of transformers. In the beginning, the construction of transformers, I have shown the core type of three-phase transformers, right? So there are two ways of doing it. So let's say if someone goes by three phase or someone goes by the bank of three single phase transformers, then the problem with that is obviously it will take a lot of space because the core requirement, winding requirement, everything has increased there, okay. But the benefit and it would be then obviously then it would be costly as well. But the benefit with this three phase transformers is, first thing is the, let's say in case of any fault, so even if you want to remove, let's say in one phase some fault has occurred, so you can easily remove one particular transformer which has faced the fault situation, and you can replace it by another single phase unit there, okay. But obviously now again to keep the multiple units of three single phase transformers would also be a costly affair then, okay. But the other benefit you can see is in a situation where you cannot carry your entire three-phase transformer, the one bulky unit. So what you can do is you can have three smaller unit of single-phase transformers, and after reaching there in a particular in that environment where you want to put your three-phase transformers, you can put it there easily. You can make those three single unit transformers into one, and you can use it there. So there are actually two ways of doing it. Other way is using single unit of three-phase transformers. Since this three-phase transformers is widely used in our power system network, so we will be discussing about it as well, some important aspects of it. This may be core type or shell type. So obviously single phase transformer also will have a core type or single or shell type arrangement, right? Okay, so that means like you have three units of single phase transformers, and the winding of it you are using it to connect a three phase transformers, okay. Obviously for the connections as well, let's say bushing requirements are there, right? For a single phase transformer, like the bank of three single phase transformers, there you would be having at least I would say 12 bushings, right? 12 terminals, and terminals are bushings only, right? uh, so that would be a costly thing then. But if I'm using a single unit of three phase transformers, there I would be having only 6 terminals, okay. So this is very well clear, right? Okay, the bank of single phase transformers is actually the single phase transformer. It can be core type or shell type, but the single unit of three phase transformers generally we prefer to be core type, okay. So in the core type, uh, if you see here, I have shown the let's say if I make this kind of core arrangement where each limb is at 120-degree phase apart, and on each limb we have the primary as well as the secondary winding. On each limb here only, in this section only we have the primary and the secondary winding, okay, primary and the secondary winding on each limb. So obviously if you see this section here, if I energize it from this source, let's say a current source here, if I energize it, the flux produced by it will actually see the reluctance path here as well, here as well, but the minimum reluctance part would be this, the nearest to it, and most of the flux will go through this branch, right? And in this, let's say if I energize the other phases as well, so in the center limb of it, if you'll see, the net flux, the sum of net, all these three flux would be 0. So phi A plus phi B plus phi C, they would all be in 120-degree phase apart, so it would be 0. So as we know, in a three-phase connection or balanced connection, if you remember, star star, let's say balanced connection, so we don't needed a neutral wire to be connected there because the sum of the neutral current was 0 there, right? IA plus IB plus IC is 0. So we said, okay, we won't need this neutral wire, and we simply that we have altogether like I would say eliminated that neutral wire there, right? In a balanced condition, star star. Same thing if the flux here in the central limb, in this limb if it is 0, so we can replace it, right? So if you see here, so if we energize the winding on these limbs, actually on all these limbs, if we energize it, so this will take, because this and the center, the flux is 0. So I would say at this node, the sum of all this flux phi A plus phi B plus phi C is 0. Now this kind of construction is difficult to make, right? You think you have to design it in a 3D construction of it. So it would be difficult to manufacture. Okay. So only advantage with this kind of arrangement is you will get the flux balanced here. Okay. So if the flux are balanced reluctance, same reluctance, every source is seeing the same reluctance path, then the magnetizing current which is drawn from the source, that would be balanced. But this is very difficult to manufacture. So we avoid this kind of construction. Rather, we use this kind of construction. So you can think of that we have pushed this B phase towards the center of it, and you can think of that this has been made in this way. Okay. So obviously the flux here, let's say flux produced by winding A, phi A, right? So let's say if you don't energize the other two phases, so you can see that this flux will get divided here and here, right? Okay, this was the problem which I have given in the magnetic circuit, uh, the tutorial, the very first problem there, right? So here at this node, if you'll see, the sum of flux phi A plus phi B plus phi C, it would be 0, right? But in each limb, if you'll see, if all the phases has been energized, then you can think of, let's say phase B has been energized and it is producing flux here. So it will get divided here and it will get divided here. Okay. So in this limb, if you'll see, phi A is in this direction upward, phi B would be in this lower direction. Let's say I have assumed the dots here. Okay. So so in each limb, if you'll see, the flux, I would say the net flux, if you'll see on limb, in each limbs, if you'll see, that would be phi A. Let's say for limb A, I would say, if I mark this limb as limb A, so there it would be phi A minus phi B by 2 and minus phi C by 2. Okay. Similarly, for the other limbs also, you'll see that this expression is coming. Okay. And assuming that the net reluctance is 0, the permeability is infinite, then in that case, if you calculate this magnitude, will come out to be I think 3 by 2 of phi m. If you solve it, let's say phi m at an angle, phi A is phi m at an angle of 0 degree, phi B is phi m at an angle of minus 120, and phi C is phi m at an angle of plus 120 degree. So if you solve it, if you do the phasor sum, I think this magnitude will come. Okay, 3 by 2 times of phi m. So that means simply, right, you can draw the phasor diagram. It's easy to solve. Let's say in this diagram only. So phi A is in this direction, phi B would be because here we see phi b is, if it is in this direction, phi b by 2 would be in this direction, and phi c by 2 would be in this direction, right? So net resultant, if you'll see, it will come out to be phi a plus this magnitude of phi b and this magnitude of phi c. Okay, so this net magnitude, if you'll see, it would be a little higher. That's why in this kind of construction, what I said is even the winding requirement, the number of turns requirement would be less. If you remember that induced EMF, I said, right, is 4.44 F phi m N1, right? Induced EMF, let's say, for the primary winding. So now overall flux has actually been increased here. So if I say E1 by N1 or induced EMF per unit turn, induced EMF per unit turn, if you will see, for single phase, it would be, if this is for the single phase connection, then for same number of turns, if you will see, it would be, let's say, if this is for single phase arrangement, for 3 phase, if you'll see, that induced EMF number of unit, the induced EMF per unit turn would actually be 3 by 2 times of phi m. That means if I want the same number of, if I want the same amount of voltage, induced voltage, then in that case I can reduce my number of turns as well. This 3 by 2 terms can come here, right? So that equivalent amount of number of turns we can reduce to get the same amount of induced EMF there. And obviously the flux produced here, that will depend upon the applied voltage, right? So the moment I have applied the voltage, the flux, and if all the phase voltages has been balanced, then the flux produced in each limb would be balanced. Only difference is in a practical transformer, because of the difference in the reluctance seen by these sources, there would be difference in the magnetizing current IM drawn from the phase. And during loading condition, that unbalance in the magnetic component IM A, I would say, let's say for phase A, IM A, then for phase B, IM B, and for phase C, IM C. In this condition, that they won't be actually balanced. Okay, the magnetizing current won't be balanced with this kind of arrangement. With this kind of arrangement, magnetizing current would also be the magnetizing current would be balanced, but it is difficult to manufacture. But with this kind of arrangement, the magnetizing current is unbalanced, but the construction is easier. And apart from that, we will get more number of, I would say, the induced EMF, more amount of induced EMF per unit turn. So if I'm getting more amount of induced EMF per unit turn, that means I can reduce the number of turn to get the equal amount of the phase voltages. Okay, so that's why I said that this kind of arrangement will actually save me the copper and save me the iron material as well. Okay, so that's why we prefer this kind of arrangement. Okay, so first what I will do is I will discuss about the various connections of the transformers, but I will consider the cases of a single the bank of single phase transformer, bank of 3 single phase transformer, and obviously single unit of 3 phase transformer. So first I will discuss the concept, various connections in a 3 phase transformers based on the bank of single phase transformer, because that is easy to comprehend, and same concepts can be equally applied to a 3 phase transformers as well. So you can see that like the primary winding and the secondary winding, they are wound on the same limb only. They are wound on the same limb. If this was, let's say, the low voltage winding, LV winding for phase A, okay, this is for phase A, this would be for phase B, and this would be for phase C. Okay, if you see that this is the, if this is the primary winding or the LV winding, this would be the high voltage winding, as we have discussed in the beginning of this lecture, lecture on transformers, the construction of it. Okay. Okay, so we will discuss about the various connections of transformer based on this three single phase transformers. Okay.